Hello, and thank you for joining us for today's webinar, Racing to the Finish with Additive Manufacturing. My name is Kim Kaloran with Stratasys, and I'll be your host for today's event. In this webinar, you'll learn why Joe Gibbs Racing brought additive manufacturing in-house to improve their concept-to-car process, including how this technology fits in with their other technologies like CNC machines. You'll also hear a few stories on the ways they use the technology besides just as concept models and prototypes. Before we get started, for those of you who aren't familiar with our company, Stratasys makes additive manufacturing systems that produce prototypes and production parts directly from 3D CAD files. Using patented FDM technology, our Dimension 3D printers and Fortis 3D production systems build models layer by layer using engineering-grade thermoplastics. This allows users to build real working models that they can see, feel, and test. By modeling early and often throughout the design process, you can find flaws earlier when it's least expensive to correct them. We also operate Red Eye On Demand, which is an online rapid prototyping and digital manufacturing service. So, without further ado, I'd like to introduce our two speakers. We have with us today Mark Bringle, who is the Director of Technical Sponsorship with Joe Gibbs Racing, and we also have Scott Temple, who is a mechanical engineer at Joe Gibbs Racing. Welcome to both of you, and Mark, I will let you take it from here.
Thank you, Kim. Joe Gibbs Racing is one of the premier organizations in NASCAR, currently fielding 3 NASCAR Sprint Cup Series teams, 2 Nationwide Series teams, and a driver development program. We employ over 450 people in both our facilities, which equal about 400,000 square feet of race shop in the Huntersville, North Carolina area. In the past 10 seasons, we currently have 3 Sprint Cup Series championships and have posted over 100 NASCAR wins just on the Cup side. We have sponsors like Home Depot, which started in 1999, Federal Express, which started in 2004, and the M&M's Mars company that started in 2007. Our company was started and founded by Super Bowl champion and NFL Hall of Fame coach Joe Gibbs of the Washington Redskins, which started the organization in July of 1991. In our facility right now, we currently have an engineering program that consists of about 43 engineers. We have heavy fabrication, which actually builds the chassis here in our shop. Each chassis builds some 100 feet of steel tubing. And then our fab shop, which actually hangs the bodies of the cars. Fabrication utilizes heavy stamp talent to create a aerodynamic bounce for the car's bodies. We got an engine shop, which will produce around 320 motors per year for all of our different teams. It also highlights a 7-post rig, and then a pit crew training facility, which consists of 21 pretty much athletes and 2 training coaches. Our Joe Gibbs Racing Total Live event graphic representation, so here it shows you all of our motocross teams, our show car teams, our nationwide programs, and our cup programs pretty much touch every square inch of the country. I think there's only about 3 or 4 states that we actually don't have any live activity in. Joe Gibbs Racing has the 3 cup cars, which is Joey Logano in the number 20 Home Depot car, and we got Kyle Busch in the 18 M&M's car, and then we got Denny Hamlin in the 11 FedEx car. One thing that we implemented years ago was a concept-to-car program, which we started utilizing our engineering talent. And in racing, the quicker you can get your competitive edge to the car, the better off you are. We can't rely on traditional manufacturing for 4 to 6 week delivery times. So we had to implement a program to get, when we found a really, really good idea, how to get that idea to the car as quickly as possible, and we call it concept to car. So what we did was we implemented a CNC department that we do all of our blocks, our pistons, our cylinder heads, our manifolds, some 900 different pieces that go in either the engine or in the race car or in our shocks. We also implemented programs with companies like Mitsubishi for laser EDM technology and also water jet technology. So once again, adding to our fleet of machines that we actually manufacture our parts with, So that way we can keep them proprietary and keep them from being outsourced and keeping the quality and quick turnaround. But one thing that happened was we found out constantly that our schedule was being, we were working 7 days a week, 24 hours a day. We were trying to find ways to actually take some of the load off of the CNC machines. And so we actually started looking at different ways to do that, and we came up with the FDM technology from Stratasys that helps us do that. And so what we do is we do all of our prototypes first. Those actually go out on the car for form and fit. And then after that, and they've been approved, they actually go in production then. And so they never hit a machine or a programmer before they've been proven out for form and fit on the cars. After we brought that technology in the building for that one use, we found other ways to actually use the product, between direct manufacturing to some components that we utilize here, to fixturing, to our carbon fiber department. We found probably 5 or 6 different ways that we can actually use the product beyond what we brought the product in currently to use for. So one thing we do through the whole process, right now we have some 40-plus technical partners that help us on a daily basis, that actually from machine tool to CNC to FDM to consumables. These companies represent over $9 million in business for us, and that's a big deal because it gives us the competitive edge to get the concept to the car quicker, and that gives us additional cash to go endeavor in engineering and other tools to make us go faster. We're very fortunate today to have one of our lead engineers, Scott Temple, with us. Scott's one of our leading forces that actually designs the majority of the components that go in our race cars and our motors and our shocks, and is a big advocate of the FDM technology. So I'd like to introduce Scott.
Thank you, Mark. So the engineering group here at Joe Gibbs, like Mark mentioned, has more than 40 engineers, and they do all sorts of activities, and one of those activities, and the majority of what we do, is design these parts from the ground up. We use our CAD models to actually make prints for the parts that will eventually end up in CNC, but before they do, most parts go to the FDM to be built, to check for form, and typically function. And we'll end up with a final part at the end of the day. So our first case study here is a steering shaft mount that we had to build after one weekend. We just decided that we needed to have a lighter, stronger part for use on the car. It's always a main advantage to take all the weight you can out of these cars. So if we see a part that needs it, we'll attack it immediately. So for this part, weight and strength, and then we do, typically on parts like this, we have constraints, time being a big one, because the faster you can put it out, the better off you're going to be and the longer you can race with that part before anybody else at the track has that. And one other thing we needed to do was make sure that this part would actually fit in a car and the size was right, because all the components that it connected to were going to stay in the same spot. So we go through many design iterations. That's the leading factor why we use FDM. It allows us to do more with less time. So here you have this first iteration part, and you can see it's very lightweight. It's structurally sound. Everything was more or less okay, but we decided we just needed a little bit more there for the end. So 6 hours later, you can have another part, another iteration, which became our final design. And we put it on the car. We knew everything would be great once it came out of the CNC shop, so we could go with confidence from there. So here you can see the final outcome. It's in the car. It's machined out of a solid piece of aluminum. We had no problems fitting it up. Everything worked great. First time it went out, and it only took 4 days to get this part from design to the car, which is key. It only took basically a week from the time one race ended to the time the next one began. Here's another part, the rear gear cooler duct. It presents a challenge on multiple levels, because you have a part that you need efficiency, you need the form to actually fit into the car, and it has to go around a lot of different parts. And one of the main reasons that we had to look at this part in the first place was we had some overheating for the rear gears, and we were actually ruining some parts in the transmission. So that's key right there. Sometimes you can't even finish races if you ruin gears. So we had to get this part out fast, but we had to do it smart and get everything in line. So we model these things in our NX5 package, and we can do iterations from there. But we use the FDM so that we can do more iterations in a less amount of time. And in this case, when you're dealing with air movement and going through ducts, you want to be sure that you have the right thing. You can't always just calculate on a piece of paper what's going to be the best. So if you can have 5 to 10 iterations, you can test them and know that everything's going to be okay once you get to the track with your 2 or 3 best, and you can test it actually at the track. So what we have here is you can see the picture of the rear gear cooler rig that we set up, and kind of the steps that got us to that point. We were able to model these things in CAD. We were able to shoot them right down to the FDM machine, build them out of the PCABS plastic that we use almost exclusively here at Joe Gibbs, and then just building iteration after iteration, we're able to take them out, just swap them basically on this rig and test them for temperature and heat and flow and everything else you could want out of this to make sure that when you get to the track, everything's going to be great. Here's an example of one run that we did on this rig. You can see the first picture, you have kind of the outlet of where this air is going to be blowing. It exits out under the car. And the next couple pictures, we actually have a thermal camera in-house that we're able to use. So the second picture, you're looking at the duct itself. You can see kind of how the air is moving and where the heat is being generated in this duct. The last picture is a picture of the cooler face, and you can get an even better idea of how the air moves through the cooler and then exiting, so you can make it disperse over a wider area and get every ounce of cooling that you can out of this. And once we have these 2 or 3 coolers that we're happy with, we're able to put them on race cars, take them to the track, which can be an expensive process, so you want to be sure that what you take is really going to count. But we're able to actually put them on the car, test it, you know with full confidence that that's going to work at the track because you're at the track. So when we run at these kind of track conditions, we see typically 170, 180 miles an hour, lots of vibration, lots of heat again. So it's good to know that the cooler can take this, the plastic duct can take those kind of conditions and excel. So once this project finally wrapped up and we had a finished part that we were happy with that we still take to the racetrack, with the FDM machine, we know we're going to have performance on our side. We will have gotten the most out of all our designs. We have options to test. It's never a bad thing to have too many options in this case. We're able to develop the part much faster than if we had to machine ducts, which is not efficient at all for this kind of project. The PCABS material that we use can handle the heat. We typically in this cooler see about 230 to 240 degrees Fahrenheit, and to know that it can handle that is extremely beneficial. And then, of course, being able to take a part right out of the FDM machine, put it on a race car, and take it to the track without having to make this duct out of any other material is always nice. So another study that we have are the brake ducts. And the brake ducts, they basically vent air coming in, and they duct that air to a specific spot on the tire or the wheel and on the brakes themselves. And the problem we were having at the time was that our tires were getting too hot, and when you're using your brakes too much, that heat can destroy your tire. You see it on a lot of weekends, so It happened to us one time, and we needed to solve that problem very quickly to get it to the track the next week. So for the FDM, like I've already kind of mentioned, it's, you can do it very fast. All you're limited by is the CAD model that you're able to create, which for us isn't a problem. A lot of our engineers know how to use this program very well. So we're able to model any kind of shape that we want, put it in the car, and test it. So for this part, as you can see, very complex shape. You would never really want to start machining this part, and especially not a bunch of them. Maybe as a one-off, but that wasn't our intent. We needed to have it for each of our 3 cars, every weekend going forward. So the FDM parts, for this application in particular, we were able to build a duct, put it on a car, take it to the track and test it, which is just great. But then when we actually need to make a part that we can take to the track, we're able to use the FDM to create molds so that we can take those molds to our carbon fiber shop and they can make usable parts for every weekend. So like I mentioned, we're able to create basically a solid buck out of these pieces, and when you get this solid part in hand, you're able to either take carbon fiber right off of it, which sometimes we're able to do, but a lot of times we can just make female molds out of fiberglass, peel it right off the FDM part, and then pull the carbon fiber part out of the female fiberglass molds, and those molds hold up for a long time, and it's never typically a problem. It's great to be able to create tooling like that out of the FDM machine for basically an end result of a carbon fiber part. So, in conclusion on this, with the FDM, the process becomes much easier. You don't have to worry about CNC time. That part that you've seen, all those parts that you've seen would definitely require a 5-axis machine, and that's very valuable time that we try to keep open in the CNC shop for different projects. So to grow it in the machine is great. You have fantastic turnaround time. I mean, you model it in, a number of hours, and then you're able to grow it in the same day, or build it, in the same day. Then that's great for us. The fact that it can be used multiple times throughout the process, you have your prototype, and then your mold capabilities out of that really helps us out so that we can keep all our tolerances the same. We know just how to build these to get a carbon fiber part in the end. Here's a pretty innovative project that we used the FDM machine for. We had some Nakka Ducts that go in our rear windows, basically, and sometimes we were having the fabricators actually make each duct and trim it and pop the holes in it. And if you had 2 different guys doing this at a time, there was always the possibility that the holes wouldn't quite line up. You had a lot of wasted material, and it didn't work out really well. So what we were able to do is we could scan one of these ducts, take it into a CAD program like NX that we use, and actually make a fixtured piece that could hold these Nakka Ducts while they were sitting in the water jet, and it would cut them the same every time, pop holes in them, and they would line up to the windows. That was the goal. And once we figured, hey, let's build these fixtures out of FDM, it makes sense. They don't degrade over time. They're strong. It'll work just fine. So that's the route we went with this. So as you can see here, you have your fixtured pieces on the bottom. They're bolted right to a plate. You can put that plate on and off the water jet as you need it, and you know that it's going to be the same shape every time because it's just a program basically for the water jet. The Nakka Duct slides right in there. It's a complex freeform shape, but we know that it's good with the scan and the CAD data. It'll just drop right in. So it locks it down. The water jet cuts it, and then the final picture there, you can see that we can just snap a duct right up to the window riveted on, and every time it's the same. You don't have that wasted material. So the benefits that we saw out of this project were the accurate setup. That was key for us. You know, we could do 2 at a time. It's a very fast cut because it's plastic that we were cutting. You have less waste due to human error on the fabrication side. You have confidence that what you're going to do is going to work every time. There's no confusion when that part comes in, and just no mistakes, and it opens everybody's time up when you don't have any mistakes like that. So it worked out great. Here we have a part of our chassis that we designed and developed. We needed something stronger. It needed to be the same every time. So, of course, the same process happened. We modeled it, and then we grew it in the FDM machine to make sure that everything would actually work. So you can see kind of the general scale of this part here. And I'll talk a little bit about how it saved us on CNC time and just really got the part faster to us. So we'll kind of compare the traditional method versus using the Fortis machine. In this particular instance, we ended up with 5 different revisions to the part. So if you're going to do it traditional method versus the FDM you can see here has many less operations. I mean, you have one real operation. It's just the building on the FDM machine compared to traditional manufacturing where you have to set up the part differently in each machine to get what you want out of it. There's no programming or setup or design and machining for the FDM machine, so that saves you nearly 60 hours there. And then the build time is considerably less for the FDM machine. So total, you're looking at 76 compared to 16 hours. And in our world, that makes a world of difference. So for 5 different revisions, we're able to do 1 week for an FDM part to where it would have taken 5 weeks for a traditional manufacturing. In this case, it's not very realistic for us. You need something faster to solve your problems to take to the race. So for the cost is another thing we look at. It was obviously a very huge savings, about $22,000. So that's always nice to have back. A couple case studies we have here are parts that go straight from the Fortis machine into our hand and actually usable. So the first one we'll talk about is an electronics box, where this box it's just going to hold wires and switches, but we need to have it. It needs to bolt to the car when we go out and do testing at the track. So we were able to go through multiple design iterations in our CAD package and feel confident that the geometry was right and everything was going to fit that was going to go inside it. So we were able to get this part straight out of the machine. We had it in hand, we wired it all up, and it was great to just throw on the car, and it's strong enough to withstand, again, all the vibrations and all the conditions that go on inside a car. The second case is a heater control box, and it had the same kind of function that the electronics box did. It was going to hold wires and switches and gauges in it, but we were able to scan a car door that eventually became the back face of this control box, and we could put it in CAD. We knew it was going to conform right to the door when we finally made the part. And again, we were able to just build one of these parts, take it right out of the machine, wire it up, and put it on a car for race weekend. So another thing that we use these FDM parts for is as communication tools. And what that means is that we're able to grow one, or we're able to build one. We're able to give it to the guys on the shop floor, and they can know kind of what's going to be coming downstream when an actual part does get made out of the CNC shop. So this demo part you see here is a brake caliper, very complex. We need to make sure that it's right before you would ever start machining one of these. So it's great to be able to give them, and they can let us know that it will actually work. So here you see a couple different guys. The picture on the left, this is one of our mechanics on the 18 team, and he's able to hold the part, fit it up to the car, make sure all the tools are going to work when he actually goes to work on that particular piece, and that it fits around the brake rotor and the wheel and everything else that goes into that assembly. The guy on the right, he's one of our CNC operators, and time and again we have prints that are just too complicated, and we get a lot of questions after the prints are made. So by having the part in hand, he's able to measure certain dimensions and do what he needs to do to keep rolling on machining that part once it gets to that stage. So again, the benefits are that everybody works off the same part. There's no confusion there as to who's got what part, and maybe there's different iterations out there. Everybody's got the same thing. You can prep for the installation. There's no machining errors. You know this is going to be exactly what comes out of a CNC machine because the FDM machine is so accurate. So finally, after doing all these parts, and the engineers have spent a lot of design time on them, the main goal is to end up in Victory Lane every weekend, and this is one of our weekends at Bristol Motor Speedway this year where Kyle ended up in Victory Lane. So that's always a great sight to see.
Thank you, Scott. That was great, and thank you, Mark, for your presentation earlier. In just 1 minute, we'll take some questions that have been coming in during the presentation. If you have a question in the meantime, please be sure to submit it through the chat panel. After the event today, you can go to this URL, www.stratasys.com/Joe Gibbs Racing, and there you'll be able to download a copy of this recording along with some case studies, different applications, and also request a free sample part. Okay, well, it looks like during the presentation a couple of questions have come in that we have some time to take live now. Okay, here's a question from Jerry who asks, how often do you have to produce new cars? Mark, Scott?
Well, that's kind of a tricky question because what we do at Joe Gibbs Racing, a lot of things is out of our control as far as what happens on the track. So if we have good fortunes on the track, we don't have to produce a lot of new cars. But then if there's new technology that we find in the chassis or the bodies, then we will start a production of new cars and kind of filter the older cars out on the back end. So depending on what happens on the track and depending on what we come up with here in the shop, will kind of dictate how many new cars we build per year.
Okay, thanks. Here's another question that came in. This one is from Peter. How many parts do you run on your FDM machine?
So it's hard to kind of give you a real sound number here, but to ballpark it, we do hundreds of parts a year. And more than that, you can have parts that range in different sizes, but the main point is that we run this thing 24/7. There's never really a minute that it's down. If it is, our engineers scramble to put something else on it because there's always a design to be made. It kind of depends if you're making a small little switch or a housing, or if you're making a whole intake manifold, which we do. But I think the main point is that we use it all the time.
That's great to hear. Looks like we have time for one more question. Kathy is asking, do you add actual FDM parts to the car?
So I talked a little bit about during the presentation about putting parts on the car, taking it to the track tests, and really that's about all we can do for the FDM parts. NASCAR has a lot of rules and regulations about what kind of materials you can and can't use, and unfortunately we can't take a lot of these FDM parts to the racetrack on weekends only to stay within the rules. But we run these cars a lot that doesn't have to do with a race weekend, and we use FDM whenever we can because it's just a much simpler and faster way to go.
That makes sense. Thank you all for your questions. If we didn't get to yours live on the call, we will follow up with you via email, but now we are about out of time. We would like to thank you each for your attention during this presentation, and thanks again, Mark and Scott, for your words of wisdom. And now I'm going to turn it over to our operator who will close out the session.